Welcome back to Part 7. In our last section, we mapped out the critical human error and signaling pathways under our manual valve branch, and we used the Item Toolkit's page flag feature to clean up our main design canvas. Now, we are ready to continue our deductive analysis and complete the remaining logic for both input streams. Before we modify our layout or dive into the subpages, this is a perfect time to save your project. Simply click the Save button located in the main toolbar or press Ctrl+S on your keyboard to ensure all your hard work from the previous session is securely saved. Keeping a habit of saving frequently prevents any data loss as our logic trees grow in size. I have already saved the project on my end. If you are following along with this tutorial, please take a moment to name your project, reactor vessel, and save it directly to your designated project folder. Now that our file is saved, let's navigate into G-Input 1 subpages and finish building out the safety logic for our system. Let's move on to GEV1, which models the failure of electronic emergency valve 1 to close. What are the immediate, direct causes for this failure to occur? Looking at our system layout, it can happen due to one of two main pathways. Either the physical electronic valve itself suffers a primary mechanical or electrical fault, which is a basic event from our table, or the valve functions fine, but the controller operating it fails. Let's create a new subgate for the controller pathway, naming it G-Control with the description Electronic Controller 1 fails to issue close command. Since the failure of either the physical valve or its controller will cause the emergency isolation path to fail, the logical relationship here is in OR gate. Next, let's look at G-Control. Why would the controller fail to issue the shutdown command? There are two direct causes. First, the controller hardware unit itself could experience an internal card or power failure, which is a basic event in our table. Second, the controller might be functional but fails to receive the activation signal from the sensors. If we look closely at our system diagram, we will notice something very important. The emergency activation signal is actually shared between the manual valve alarm path and this electronic valve controller path. We have already completely modeled this exact sensor logic under the G-signal gate in the MV1 branch. Since this represents the exact same physical subsystem, we do not want to recreate it from scratch. Instead, we can use another powerful feature within the Item Toolkit designed for redundant or shared components, the Repeat Transfer Gate. To implement this, navigate back to the G-signal gate we created earlier in the tree. Right-click on it and select Copy. Next, return to our current branch, right-click on the G-Control gate, and select Paste Repeat. The toolkit instantly creates a mirrored copy of the entire G-signal subtree beneath G-Control. This linking mechanism ensures that if you change a parameter or a calculation property for a sensor in one part of the tree, it automatically updates across all repeated instances, maintaining perfect consistency throughout your risk model. This completes the path for GV1. Now let's go back to G-Input 2. Once we finish the modeling for G-Input 1, we can reuse a lot of existing elements we already created. Now, let's turn our attention to the second input stream, G-Input 2. You'll notice that the architecture of this stream mirrors our first line perfectly, which allows us to build out this branch efficiently. G-Input 2 has two direct causes, the manual valve branch, GMV2, and the electronic emergency valve branch, GV2. Just like the first stream, both of these valves must simultaneously fail to close in order for input stream 2 to remain open. Therefore, the logical relationship here is an AND gate. Let's drill into GMV2. The direct causes for this manual valve to fail are either the physical valve itself mechanically jamming, which is our MV2 stuck open basic event, or the operator failing to respond to the emergency. Since the operator's failure pathway is identical across the system, we can reuse our work. Let's navigate back to the GOP failure gate we fully developed under the first stream. Right-click to copy it, then right-click on GMV2 and select Paste Repeat. Just like that, the entire human error and signaling subtree is linked here, and we are completely done with the GMV2 branch. Next, let's look at the electronic valve branch, GV2. Following the exact same logic as GV1, this pathway fails if either the physical electronic valve fails to close or its controller fails. First, we will add the primary component fault for the physical valve, which is the electrical valve 2 failure. Second, we need to account for the controller failure. Because the controller's subsystem logic and its shared sensor inputs are identical to what we just built, we can reuse that subtree as well. Let's find the G-control gate from our first stream. Right-click to copy it, then right-click on GV2 and select Paste Repeat. With a few strategic clicks using the Repeat Transfer Gate feature, we have successfully modeled a highly complex, redundant system while keeping our fault tree perfectly consistent and mathematically linked. That brings us to the completion of our full fault tree structure for the reactor vessel system. In this section, we move from high-level system boundaries down into the granular root causes of failure. By applying the deductive construction rules from Part 4, we systematically broke down our top event, G-explosion, layer by layer. We explored how to evaluate serial and parallel dependencies to choose the correct logical relationships, translating physical system characteristics into and/or gates on our canvas. Along the way, we utilized two of the item toolkit's most powerful efficiency features: page flags, transfer gates to segment our complex input streams into clean, dedicated workspace pages, keeping our top-level model highly readable. Repeat transfer gates, to seamlessly clone identical subtrees, like our shared G-signal loop and GOP failure human response pathways, ensuring absolute consistency and mathematical alignment across redundant system lines without duplicate data entry. At this point, every single branch in our tree successfully terminates into a defined basic event, meaning our qualitative model construction is complete. Now that our system logic is fully mapped, we are ready to move from qualitative structure to quantitative analysis. Make sure to hit save one last time. Thank you for watching, and I will see you in the next section.